I'm going to talk about sort of our work in using machine learning to improve sort of the variational Monte Carlo or the variational method in sort of pursuit of solving or resolving questions in quantum many-body problems. And much of the work that I'll talk about today have been done by two of my students, Dmitry Kokov and Diderot. Okay, so today mainly we'll be discussing the variational approach, but I thought I'd spend one slide just mentioning some of the other things that we're working on, kind of in the broad area of, if not quite machine learning, machines learning. In addition to this variational approach work that I'll be talking about today, we've been interested in sort of pushing forward some ideas on inverse problems. So typically in variational Monte Carlo, you take a Hamiltonian and you find a ground state, get symmetries, observables, operators out of it. We have some new techniques that we're excited about where you start with some wave function, start with some set of symmetries, and pull out all the parent Hamiltonians. We've been doing a bunch of machine learning working with some experimentalists, Pinchane Huang and her group, on analyzing STEM image data. We have some nice work looking at automatic basis rotations to sort of mitigate some sign problem issues. We can do this in sort of large 2D bulk systems. With Juan Carscuala and company, we had some work on using transformers for simulating quantum circuits. And we've been doing a variety of other work sort of in the arena of BQ and such. Okay, but that's not my focus today. My focus today really is the variational problem and the variational approach. And just sort of operationally, today I'll be talking a lot about variational wave functions. And as an operational definition, we'll just think of a variational wave function size as a black box. It eats configurations, maybe the position of the electrons or which spins are up or down, and it spits out an amplitude. And then in the variational approach, the whole name of the game is that what you should do is you should work with some family of variational ansatz, some variational wave functions, and you should optimize over that family. In particular, you would typically optimize the energy over this family of wave functions. And sort of through the history of wave functions, there's been many, many different sort of wave functions, but we can think of them broadly in a couple of classes. They're sort of dressed mean field states. So maybe the original wave functions were mean field, some sort of Hartree-Fock thing. And even to this day, these wave functions are very powerful. You dress them sort of canonically as with a Jastrow term. So you work with some Slater-Jastrow determinant of some matrix. That matrix is filled up with single particle orbitals. And there are all sorts of variants of this: BDG Jastrow, multi-determinant, backflow, Pfaffian Jastrow, et cetera. And even now, sort of an ab initio quantum Monte Carlo, Slater-Jastrow are sort of a de facto wave function. When you're looking at spin liquids, projected Slater determinants are wave functions that are extremely powerful. Partons are extremely useful. And so even to this day, sort of the dressed mean field state, starting from some mean field starting spot, is a very useful thing to do. And if you allow sort of this to include multi-determinants, this set of state is universal. So what I mean by universal, well, if you sum up enough determinants, you can represent everything. Now, of course, by a counting argument, the number of determinants you need for arbitrary states is exponentially large. Another broad class of wave functions is tensor networks. So instead of starting from a mean field, they start from a low entanglement ansatz, starting from something like a product state and then turning on entanglement slowly. And so there are a whole zoo of these: matrix product states, PEPs, mirror, et cetera. Also, these are universal if the bond dimension is large enough. So you crank up the matrix size or the bond dimension of the tensor, and if it gets big enough, it can represent anything. Again, big enough is going to be generically exponentially large. One of the new things that this has brought sort of to the table is that the optimization is not done by variational Monte Carlo, it's done by linear algebra. And one of the other nice things is that you can represent states in the thermodynamic limit. So you can have a matrix product state, an IMPS, where a single tensor A represents any arbitrary system size. So more recently, there's been a lot of work on neural network states, starting with some very nice work by Giuseppe and company, where they used RBMs to represent a variational ansatz for a variety of spin systems. And again, just like these other two methods, this is universal if the number of neurons is large enough. Again, in order to be representing an arbitrary state by a simple counting argument, you need an exponential number of neurons. This optimization is typically done by the standard variational Monte Carlo technique, although we've been trying to sort of push on that a little bit and improve some things. It's interesting, this thing can also represent things in some sense in the thermodynamic limit. So we had done a couple of years ago a nice calculation. We took a deep convolution neural network as a variational wave function. And what we did is we optimized it at 40 sites. This is a simple model, a 1D Heisenberg model. And then we just asked the question, given those same parameters, you can use that same variational ansatz to represent 100 sites, 20 sites, 80 sites, et cetera. And we found that the variational energies optimized at 40 sites actually represented the rest of the variational ansatz really well. The fact that it represented large systems is actually nice and was useful, but the thing that actually surprised me the most is that if you looked at the 20 site and the 10 site energies, they were really smack on. So this is the 10 site variational energy, and this orange line is the exact answer. This is the, sorry, that's the 20 site. This is the 10 site variational energy, and the dotted line is the exact answer. So it's pretty impressive that for all energies, this does a good sort of variational representation. Okay, so now, I mean, these neural networks are sort of new, and really sort of the question is, how good are they? And more generically, can we understand how to build better architectures, how to optimize them better, things like this. So we did some work where we looked at sort of a bunch of different variational wave functions using different machine learning architectures. Many of these sort of machine learning architectures that at the time that we posted this paper had not been looked at before. So things like ResNet or multi-RBM or FIFO or neural nets with RBM on top, et cetera, et cetera. We represented these all as computational graphs, which is sort of common in the machine learning community and sort of a nice way to think about things. And we also sort of used these computational graphs to represent Slater determinants, projected BDG states, matrix product states, et cetera. And so then we just asked a question, sort of simple 1D, 2D Heisenberg models. We just looked at how well they did. And sort of the upshot of these graphs is that for the 1D and 2D Heisenberg model, everybody sort of does things kind of in the same ballpark. So everybody gets down to similar energies. Some are better than others. But sort of the upshot of this is there are lots of different ways of combining these machine learning architectures to get reasonable energies. But they're reasonable, but kind of in a similar ballpark as, say, projected BDG and MPS. We have a nice code if you also want to go and write a multi-RBM times a Pfaffian with a Jastrow on it or something. We have a nice sort of prototype code that you can download, and in 20 lines, these circled red lines here, you can add your own wave function. This is actually the projected BDG wave function, which is actually one of the harder ones to do because it's not sort of a typical machine learning architecture thing. And it does all the backpropagation and everything for you for free. 20 lines, you too can run your own favorite variational ansatz. Okay, so again, in sort of this pursuit of trying to understand how good these neural networks are, that was a reasonably simple model, 1D and 2D Heisenberg models. The sign structure isn't very complicated, although there is the Marshall sign rule that we were able to capture with some of those wave functions without dialing it in. So now we can go and we can do a little bit of a more sophisticated analysis. We can look at wave functions with complicated sign structures. So what thing are we going to use there? Well, RBMs can't even get the sign structure right without complex weights. So really, we chose, in this particular study, a feed-forward neural network. We chose a Heisenberg model, but on the Kagame lattice. So this is a complicated thing. And we just did, we didn't do variational optimization. We're not looking at the energy at all here. We just did very tiny systems. We solved them exactly. And then we tried to match as best we could, this is optimization by graduate student, the exact diagonalized state with a feed-forward neural net. And that's what we've done here. We crank up the number of neurons. This is for depths 1, 2, 3, 4. This is log 1 minus fidelity. So smaller is better. And there are sort of 4 takeaways. One is that you get exponential improvement with neuron number. That's great. That's sort of a necessary condition for things to work well. Depth doesn't really help. You hear a lot about deep learning. In this particular case of the feed-forward neural network, depth didn't really do much for us. As long as you had a given number of neurons, you got similar results. Sort of just as a benchmark, to get 24 to 30 sites required a lot of parameters, 10 to the 4 parameters, to reach something like 85% fidelity. So that's good fidelity, but not amazing fidelity. We get equally good fidelity in spin liquids using partons and things. We just did an analysis. We said, look, learn the wave function with signs, learn the wave function without signs. It shouldn't surprise you, but it's sort of good to validate. Learning the wave function with signs is much harder than learning the wave function without signs. What I mean by much harder is I mean that for a fixed number of neurons, it's harder to represent. Your fidelity is worse. Okay, so this is not my work on this slide, but lots of other people have also looked at frustrated magnets and various things with various sign structures. So this is J2, J1 frustrated magnet square model, square Heisenberg. We just heard a nice talk about this. And those energies are pretty good, but they're not much better than partons. They're sort of competitive on the same order as partons. People have also looked a little bit at Hubbard models. So they've done partons plus RBM Jastro was done by Amada. Again, not too bad, but because you're really just doing a Jastro, you're not beating sort of standard partons significantly. So in the rest of the talk, I'm going to tell you two things. So neural net wave functions have been improving over time, and they are becoming more and more powerful. But I think one of the things that has been particularly difficult, and we heard this a little bit in the last talk, is dealing with complicated sign structures and dealing with fermions. And so we have a slightly different approach to this, and that approach is using a backflow approach. And then later in the talk, in the last couple of minutes, I'll tell you about a new way of doing optimization, a way to essentially get stochastic reconfiguration sort of optimization at a much lower cost and pain. Okay, so let me start with the neural net backflow work. So really, there are various related works here. So backflow has been around a while. So this is the first work that did it with fermions, and then lattice backflow was done by Sandro and company a decade or so later. And then more recently, Marcus Holtzman, we heard a beautiful talk yesterday, used iterative backflow. And iterative backflow, overall, the way it worked is Marcus thought very, very hard and said, here's how we sort of analytically sort of improve backflow. And we've done the opposite. We've not thought hard. We've made our machine think very, very hard. And we said, look, what we're going to do is we're going to do backflow, but we're essentially going to parameterize the backflow by a neural network. Okay, and so that's today's talk. That's what I'll talk about today. And then there's been some really nice work about a year later, and we heard two great talks about this yesterday, where they generalized this idea and they came up with different neural networks that worked particularly well, replacing the backflow parameterization for quantum chemistry problems. Okay, so we know how the standard Slater-Jastrow works. You have a up determinant times a down determinant times a Jastrow. You have some kind of spin configuration. You have some static single particle orbitals, and you evaluate the locations of the spins, say the up spins here with respect to the up single particle orbitals. You get an up Slater determinant, you take the determinant, etc. Okay, and what we're doing in neural net backflow is actually the same thing, except the following. Our single particle orbitals are no longer static. Those single particle orbitals depend on not only the location of R1, but the location of all the electrons. And to decide how these single particle orbitals should depend on the locations of all the electrons, what we're going to do is we're going to stick a neural net here. So the neural net eats the spin configurations, who's up and who's down where. It churns, and then it generates for us a set of single particle orbitals. Those single particle orbitals are then used for that specific spin configuration to generate the spin up determinant. Okay, so this is what we're doing. This is what we call neural net backflow. And we have one neural network per spin. So this is the spin up neural network. We also have a spin down neural network. They both take all of the electron positions. So there's some nice properties about this. It can trivially represent the Slater determinant, the static Slater determinant, by just setting the biases here. So if you set the biases here correctly, you can get the Slater determinant back. The standard lattice backflow involves looking at sort of holons and double-ons, and we have sort of an explicit construction where you take the standard backflow, turn the crank, and can produce one of these neural net backflows. We're not using that. It's just sort of a proof of principle, but there is such a construction, and it produces a reasonably simple neural net. So if you want, you can start with the standard backflow. This, just like multi-determinants and other neural net states and tensor networks, can theoretically represent anything. So if you just crank up these number of neurons enough, you're going to be able to get any state. It's not a super useful statement because you might need sort of an exponential number of neurons. The main downside, the main sort of thing that is unfortunate about this approach is that it's a bit costly. So it's order n to the fourth per sweep. So if you're sort of a typical variational Monte Carlo aficionado, a typical sweep for something like a Slater-Jastrow would be order n cubed. So this is a factor of n more expensive than the standard variational Monte Carlo. And the reason for that really is that when you're doing these single particle moves, you would typically be able to use update formulas in a standard Slater-Jastrow. But here, we're changing the entire matrix. And so when we change the entire matrix, what that means is that you have to reevaluate the determinant at every step. Great. So this is the high-level method. And now what I'm going to do is show you some benchmarks about how well it works. So this is some work on the 4x4 Hubbard model. So Sandro said in the last talk, look, neural networks have not really been very successful for the Hubbard model. And here I will show you sort of an explicit example where we have actually gotten sort of neural networks combined with these ideas of partons to work really well with the Hubbard model. So this is U of T of 8. This is 0.875 doping. And we did this because this can be solved exactly. And so just to give you a sense here, this is percent error. So if you do standard Slater-Jastrow, you're sort of sitting at a 5% error. You can improve that a little bit by doing kind of a standard backflow, but you're still sitting at a 4.5% error. And now when you turn on the neural net backflow, depending on how many neurons you're willing to use, things get significantly better. So this goes from n over 4 neurons to 4n neurons, where n is the number of sites in our system. And what happens is you get systematically better as you crank up the neurons. Even with n over 4 neurons, our error is down to sort of 2.8%. With 4n neurons, our error is down to sort of 1.5%. So we're able to do this both on Slater determinants as well as on BDG states. You can do a backflow on both of these. And we've developed and done this neural net backflow on both of these. One thing that's interesting is that although the neural network on BDG starts out much better, and in fact stays better, once we get to enough neurons, we really are in a situation where the neural net backflow and Slater determinant has actually restored much of the correlation that was already existing in the BDG state. And I think that's pretty cool. What that's telling you is you're really getting even sort of BDG correlations coming out from the Slater determinant. And then if you go ahead and you say, look, let's just do the standard variance extrapolation that everyone does, you end up with errors that are on the order of 0.5%. And in fact, this variance extrapolation is extremely clean. It's much cleaner than any other kind of variance extrapolation I've seen in variational results. Okay, not only do the energies get better, but also some of the physics gets better. So one of the things that you would like for your variational wave function is you would like it to have the same symmetries. And so you might know that if you optimize the spin up and spin down determinant, often the variational wave function will break the symmetry, some spontaneous breaking of the symmetry. And the reason it will do that, there's some antiferromagnetic correlations. It want to keep the spin aparts. And so if you see here the spin up Slater determinant and the spin down Slater determinant, you'll see that there's even an anti-correlation here, where the spin up Slater determinant is large, the spin down Slater determinant is small. When you turn on neural net backflow, this goes away. So I can't show you these single particle orbitals, no longer static. But I can pick a particular correlation. This is a random correlation sample from Sci-squared. And what you see is you see that the spin up and spin down single particle orbitals look essentially the same. And this is really nice. This has really restored things. The other thing that's nice here is that we've really changed the sign structure in a qualitative way. So we've looked and we see 9% of the signs, 9% of sort of the weighted signs are different between neural net backflow off and neural net backflow on. Restores not only the symmetry of the single particle orbitals, but the symmetry of the observables. As you crank up from 8 to 128 neurons, your charge density gets much more flat, your spin density does something sane, your doublons come down. So that's one system size. We've also run in a bunch of other system size. So 16x4 Hubbard models, 12x8 Hubbard models, et cetera. There you're getting sort of variance extrapolated errors that are kind of in the order of 0.2%, 0.5%, et cetera. I should say a nice thing to benchmark against. So there's this nice Simon's collaboration result doing variational Monte Carlo in the Hubbard model. They do, say, IDMRG and the 4x∞ answer. So we run 4x4, 8x4, 16x4. What we see is we match up with the IDMRG answer beautifully. In fact, these answers are essentially as close as, say, the auxiliary field quantum Monte Carlo and the DMET answers. So this is much better than sort of the standard variational approach. Another thing that is really nice here is typically when you think about backflow, you think, holons, doublons, this is something that really wants to run on something like an itinerant Hubbard model. And we went and we ran it on some frustrated magnetism. So this is a difficult thing. This is a Kagame lattice, 4x4x3 Kagame lattice. And we ended up getting errors that were sort of on the order of 0.2%. So this is really sort of an impressive answer for variational ansatz in the Kagame lattice. So this works really well both on fermionic systems as well as on frustrated magnetism. You can also go ahead and you can try to stare at the neural network and try to extract what in the world is doing. We haven't had a lot of success with this, but these are the weights of the neurons, or the weights of the edges between the input neurons and the first hidden layer. And the one takeaway from this is the following. The spin-up neural network really wants to know where the spin-down neurons are. The spin-down neural network really wants to know where the spin-up neurons are. So that's what's going on. Not much else that we've successfully extracted from this. So that's the first thing I wanted to tell you. And we really have a way now to combine partons with these neural network states in such a way to get many of the advantages of both, to really sort of fundamentally and qualitatively change the underlying science structure, and to really start out with sort of parton quality answers and then systematically improve from there. So in the last couple of minutes, what I'd like to do is I would like to go ahead and talk to you about sort of a new approach that we have for doing optimization. How does wave function optimization sort of look through history as far as variational Monte Carlo is concerned? Well, sort of the first thing that people did, and one of the original things, was stochastic gradient descent. So you have some objective function, the energy, and you really just walk downhill. And actually, sort of in pre-ancient history, instead of optimizing the energy, people optimize the variance. And this works reasonably well, but the convergence is a bit slow. And right, the convergence is a bit slow, but it's really nice in the sense that the scaling with parameters is very good. And so there are better things though, right? So there's stochastic reconfiguration or imaginary time evolution from Sandro and company. The scaling here is not as good. I mean, it's order p cubed if you do the naive thing. You do conjugate gradients and whatnot, you can get down to order p squared. If you work extremely hard, you can get down to order p, but the constants on that are not very nice. And so it's okay, but not amazing. It's really numerically unstable. So you end up generating an overlap matrix. The overlap matrix, if you have a gazillion parameters, is ill-defined because these parameters aren't really linearly independent. So you have to realize the overlap matrix. There's a horrible undersampling problem. Your S's are actually almost always wrong. This doesn't cause so much trouble in optimization, but if you want to do, we have a nice variational finite temperature technique. And in this variational finite temperature technique, if you really want to use this, you want your S's to be more accurate than they are. So this is a beautiful method, right? And it's what everyone uses, stochastic reconfiguration. But it's also broken in a lot of ways. And it would be nice if we could get sort of stochastic reconfiguration paths, but without any of the complications. There are other methods like linear methods, same thing, not super numerically stable, order p cubed, can be made faster if you work hard, complicated, etc. And so what we've done is we've developed a new approach sort of inspired by supervised learning. So we've been using this largely for machine learning wave functions, although it can also be used for Slater, Jastrow, projected BDG, whatever you want. So how does supervised learning work? Well, you say, look, I would like to train my machine to learn something. So I'm going to give it a bunch of images. That's a cat, that's a dog, cat, a cat. And I'm going to tell it what it is. I'm going to tell it that is in practice a cat, that is a dog, that's a cat. And then it's going to churn in the background. And at the end of the day, when I give it a new image, it's going to be, aha, this new image is a dog. And that's how supervised learning works. Supervised learning is reasonably efficient. You can use Atom or stochastic gradient descent or whatever to learn things. And so we're going to play the same game. We're not going to give our configurations of dogs and cats. We're going to say, look, instead of a dog, we're going to give it a spin configuration. Instead of the label dog, we're going to say, the label is the amplitude 0.005. We'll give it another spin configuration. We'll give it a label, another spin configuration, a label. And so, great. So this is, if we have a nice labeled wave function, minor detail we'll deal with in a second, then we can just use this approach, do supervised learning on it, and we can match this wave function. So we call this approach supervised wave function optimization, and it gives us sort of a large family of interesting optimization approaches. So all one now needs is a wave function to match. Here, we've magically started with some labeled wave function, and in a very small number of iterations, it quickly matches the correct wave function. Unfortunately, what's the problem? Well, okay, if you have the exact wave function to match, you're kind of done. So this seems a little silly. So instead, our goal will be to sort of get a better wave function to match. So here's the game. We have our current best wave function. Let's say it's a neural net or a projected BGG or whatever. It has some parameters in it. And now we want to generate new parameters, optimize it. So we're going to do imaginary time evolution. Exactly. We're going to apply 1 minus tau h times this state. And we can do this exactly. It's not costly. Same cost as doing a typical simulation with local energies. And what we're going to do is we're just going to generate a whole bunch of configurations. So a whole bunch of spin configurations. Each one has an amplitude. And we're going to say, look, what we'd like you to do is we'd like you to match a new neural net, a neural net prime that has the same amplitude as this set of 1 minus tau h psi and n spin configurations. So this is an order P approach. It's linear in the number of parameters. There's no overlap matrix. There's no inverse. There's none of this. No overparameterization, no undersampling. So this is an example of how it works. You say, I would like this iteration for you to match 1 minus tau h times my state at 1. This is the fidelity coming down to sort of a 10 to the minus 2 match. This is the energy coming down. And it comes down to something that's very close to the exact imaginary time evolution. Then you say, please do it again. I have a new neural net state I would like you to match. Comes down, fidelity comes down to 10 to the minus 2-ish. Energy comes down. You say, I'd like to do it again. And you do this over and over again. The energy in between these steps doesn't have to be monotonic. You're just going ahead and you're matching 1 minus tau h times psi and n. So we call this ITSWO. And this really gives you all of the benefits of stochastic reconfiguration. These steps are the stochastic reconfiguration steps. You're doing the imaginary time variational evolution, but you're doing it without any of the inverses, without any of this work. Okay, you can play different games, right? This is ITSWO, but you can say, look, I'm not going to match 1 minus tau h psi and n. Actually, I know that if I do one of these Lancho steps, I can get to actually a much lower energy. So I can go ahead and I can do a Lancho step, and I can match that Lancho step. So I find a good alpha, I find a good beta, I match it, I update my parameters, I do this again. You could do this using diffusion Monte Carlo as your wave function. You could do this using previously optimized but stuck states. So maybe start with a matrix product state or some simpler neural network that was quicker to optimize. And this is much better tunneling. This is matching SWO. So this is a whole family of new optimization techniques that really rely on the idea that what you can do is you want to match your wave function, and that allows you to jump to the better wave function, and then you iterate this over and over again. Okay, so I think my time is about up. And so what I've told you is, well, a bunch of stuff, but sort of the two big takeaway messages is we've developed this new neural net backflow, which is really getting fermions with neural nets at DMRG level accuracy. But now we can go ahead and do sort of bulk systems, again, at a cost that is scaling as n to the 4th. That's the big downsize. And then this new optimization technique, SWO, supervised wave function optimization, which generates a whole family. You can do imaginary time evolution. You can do stochastic reconfiguration without the pain, but you can also do sort of a whole family of other things.